January 5, 1943. South Pacific waters off Guadalcanal. The early sun cast long shadows across the deck of the cruiser USS Helena as sailors moved about their routines. Radar operators bent over their scopes, searching for any sign of danger. The war in the Pacific had reached a savage intensity, and every man aboard understood that death could descend at any moment from the sky. Helena had spent the previous night shelling Japanese positions at Munda Airfield on New Georgia. Now, as Task Force 67.2 pulled back southward, the crew stayed on high alert. They had learned through bitter experience that Japanese retaliation often came swift and lethal after such strikes. For Japanese dive bombers appeared on the horizon, their outlines unmistakable Aichi D-3A aircraft nicknamed Vals by the Allies. They were older models, slower than the newer D-4Y Judas, but in the hands of veteran pilots they remained extremely dangerous. The alarm wailed across the ship, battle stations. Gun crews rushed to their mounts. The Japanese planes dove toward the American ships, their bombs hitting HMNZS Achilles before beginning to pull away. What happened next would alter the nature of warfare forever. As the Japanese aircraft climbed away, assuming they had escaped the reach of American guns, Helena's 5-inch/38 caliber batteries opened fire, but not with the frantic flood of shells that doctrine usually required. Only a handful were fired. The crews watched as the rounds streaked toward the distant aircraft, now over 4 miles away. Then something astonishing happened. The shells detonated near the planes without striking them directly. One bomber burst into flames and plunged into the sea, followed moments later by another. The gunners stared in shock. They had just seen the impossible by previous standards: aircraft destroyed at long range without direct hits. The shells had exploded automatically when close enough to the target, no timing calculations, no guessing altitude or speed, no hurried fuse setting. The weapons simply knew when to detonate. Commander W.S. Parsons, who recorded the incident, emphasized how extraordinary this was. These were not lucky hits, they were deliberate kills made by a shell that sensed its proximity to a target and exploded at precisely the right moment. The sailors had just used a secret more closely guarded than almost anything in the Allied arsenal, outranked only by the atomic bomb project. A weapon so advanced that commanders feared its capture more than nearly any other technology, one ultimately proven to be 3 to 4 times more effective than standard ammunition. Yet despite its ability to save American lives, the highest levels of command refused to authorize widespread use for nearly 2 years. This is the story of the proximity fuse, the innovation the Navy initially kept to itself, the breakthrough the Army hesitated to deploy on land, and the hidden technology that helped secure Allied victory in World War II. Before 1943, bringing down an aircraft with anti-aircraft fire was an ordeal of mathematics and frustration. The sky was vast, aircraft were small, and they moved quickly in 3 dimensions. Artillery shells, once fired, followed an unchangeable ballistic path. Traditional anti-aircraft fire used 2 kinds of fuses, both deeply flawed. Contact fuses required a literal hit, nearly impossible against a fast-moving target miles away. Time fuses had to be set to a precise moment before firing, requiring calculations of altitude, speed, direction, rate of climb or descent, crosswinds, and the shell's own trajectory. A tiny error meant the shell exploded harmlessly in empty sky. Early war statistics were bleak. In Europe it could take 20,000 rounds of anti-aircraft fire to down a single enemy plane, with some battles reporting numbers as high as 100,000. Even the best crews rarely managed fewer than 2,500 rounds per kill. Warships and ground batteries burned through mountains of ammunition while enemy aircraft kept flying. The cost was measured in destroyed ships and dead sailors. Japanese dive bombers savaged American forces throughout the Pacific. German aircraft threatened every convoy bound for Britain or the Soviet Union. Defensive fire was so ineffective it was barely more useful than heavy rifle fire. Scientists worldwide knew a better solution had to exist. The idea of a fuse that could sense its target and detonate automatically had been discussed for decades. The British had begun work in 1939. The Germans explored dozens of concepts, from acoustic detection to electrostatic sensing. The Japanese experimented with magnetic triggers. Every nation understood how revolutionary such a weapon could be, but none could make it work. The Germans pursued more than 30 proximity fuse projects, including acoustic, electromagnetic, and electrostatic systems, but all were cancelled in 1940 when Hitler demanded research focus only on technologies producible within 6 months. By the time Germany resumed such research in 1944, it was far too late. Although working prototypes were tested, none reached combat. The Japanese understood the concept but lacked the microelectronics needed. Their vacuum tubes were too large and fragile to survive the extreme stresses of being fired from a gun. A working proximity fuse would require a miniature radar set small enough to fit inside a 5-inch shell, sturdy enough to survive 20,000 g of acceleration, and robust enough to spin at 25,000 revolutions per minute in flight, requirements that pushed 1940s technology to its absolute limits. The device would need to function flawlessly in rain, snow, tropical humidity, Arctic cold, and the chaos of combat conditions, and it would need to be cheap enough to manufacture by the millions. Most experts considered it impossible with existing technology. Vacuum tubes, the basic building blocks of all electronic circuits in that era, were delicate glass containers that shattered under far less stress than artillery shells endured. Even reinforced tubes failed when subjected to a tiny fraction of the forces involved in gunfiring. Batteries powerful enough to run a radar system were far too large to fit in a shell nose. The radar antenna would need to be impossibly small yet still functional. The safety mechanisms required to prevent premature detonation would need to work perfectly every single time without exception. One failure could kill the entire gun crew firing the weapon. And all of this technology would need to be crammed into a space smaller than a coffee can, then fired from a gun with explosive force. The British shared their early research with American scientists in September 1940 through the TISAD mission, a desperate intelligence exchange undertaken as Britain stood alone against Nazi Germany. Sir Henry Tizard arrived in Washington carrying a black metal deed box that contained many of Britain's most closely guarded military secrets. Among the documents were preliminary designs for a proximity fuse, theoretical calculations, and reports on failed experiments. But British scientists admitted they lacked both the industrial capacity and the specialized knowledge in miniaturized electronics to turn theory into mass-reduced reality. Britain's factories were already stretched beyond capacity producing conventional weapons. The challenge of developing the proximity fuse fell to American researchers. The National Defense Research Committee, which had been formed on June 27, 1940, assigned the project to Dr. Merle Tuve at the Applied Physics Laboratory of Johns Hopkins University. The choice was inspired. Tuve was a physicist who had spent years studying the ionosphere using radio waves, giving him exactly the background needed for this challenge. He assembled a team of physicists, engineers, and inventors from universities and private industry. They worked under conditions of absolute secrecy that rivaled the Manhattan Project itself. The project received security classifications second only to the atomic bomb. Workers in the factories often had no idea what they were building. Components were manufactured separately with deliberately misleading names. The fuse was given the intentionally vague code name variable time, abbreviated VT, to hide its true nature even from most military personnel who would handle it. Section T, as Tuve's group became known, faced one technical crisis after another. Each problem solved seemed to reveal two new challenges. The team initially consisted of just 4 scientists in August 1940, but would eventually grow to nearly 1,000 researchers and support staff. They worked in converted buildings at Johns Hopkins and the Department of Terrestrial Magnetism at the Carnegie Institution. Security was so tight that different teams working on components often had no idea how their work related to other parts of the project. Standard vacuum tubes shattered instantly under the massive acceleration forces of gunfiring. Early tests were disasters. In one documented test, engineers fired a standard radio tube from a gun and recovered only glass powder and twisted wire. Even tubes, marketed as ruggedized and used in oil drilling equipment, failed catastrophically. The acceleration was so violent that glass would flow like liquid. Internal elements would telescope into each other, and delicate wire grids would collapse instantly. The breakthrough came through partnership with private industry. Sylvania Electric Products, working with Section T engineers, developed special miniaturized tubes with reinforced glass, multiple support structures, and shock-resistant internal components. These tubes were unlike anything previously manufactured. They started with hearing aid tubes, the smallest available, and modified them extensively. Additional glass supports were added at critical stress points. Lead wires were shortened to just 3/8 of an inch to reduce flexing. Special tungsten alloy filaments replaced standard materials. The tubes were filled with special gas mixtures at precise pressures to prevent electrical arcing under stress. but even these improved tubes failed repeatedly in early tests. In one particularly frustrating series of experiments in late 1941, 900 consecutive tubes were destroyed without a single success. Engineers tried everything imaginable. They embedded the tubes in wax, finding it melted from heat. They tried oil, which leaked. They experimented with rubber compounds that deteriorated. They tested various plastics that cracked under stress. One engineer suggested suspending the tubes in mercury, which was too heavy. Another proposed using human blood plasma as a cushioning medium, which was tested but proved impractical. The solution came from an unexpected source. Dr. James Van Allen, who would later discover the Van Allen radiation belts, was then a young physicist on the team. He suggested using a wax and oil combination in precise ratios with the tubes mounted at specific angles to distribute stress. After thousands of configurations, they found that tubes mounted at 30 degrees to the shell's axis, cushioned in a mixture of sarin wax and transformer oil, could survive about 70% of test firings. This was deemed acceptable for wartime production. The battery problem seemed equally insurmountable with conventional technology. Standard batteries were far too large and could not activate instantly. The solution, when it came, was ingenious and counterintuitive. Engineers created a tiny glass ampoule containing liquid electrolyte. The ampoule sat inert until the shell was fired. When the gun fired, the massive acceleration shattered the glass, and centrifugal force from the shell spin drove the liquid outward to contact carefully positioned metal plates. This initiated a chemical reaction that generated electrical current. The battery literally activated itself through the very forces that threatened to destroy it. It was elegant engineering, using the problem as its own solution. The radar system required innovations that pushed the boundaries of electronics technology. Traditional radar systems were enormous installations weighing tons. The proximity fuse radar had to fit in a space the size of an ice cream cone. The transmitter and receiver had to share a single tiny antenna no larger than a pencil. The circuitry needed to distinguish between the radio signal it was transmitting and the much weaker reflection bouncing back from the target. Section T engineers developed an ingenious autodyne detector circuit that could sense minute changes in signal strength as the shell approached its target. When the reflected signal exceeded a specific threshold, indicating the target was within lethal range of the shell's fragments, the firing circuit would trigger the detonation. But detecting proximity alone was not enough. The fuse had to be smart enough to avoid false triggers. A shell fired over water could not be triggered by reflections from ocean waves. A shell fired in rain could not mistake water droplets for aircraft. A shell passing near friendly aircraft had to distinguish friend from foe, though this proved impossible and led to strict usage protocols. Engineers added sophisticated wave suppression circuits that ignored long-duration signals from stationary surfaces while remaining sensitive to the characteristic reflections from moving aircraft. They built in time delays so the fuse could not arm until the shell had traveled safely away from the firing ship. The arming sequence was complex, requiring multiple conditions to be met in precise order. Safety mechanisms had to be redundant and absolutely foolproof. The fuse remained completely inert until fired. The battery contained no active chemicals until the ampoule shattered. The arming circuit required both battery activation and a minimum time of flight, typically 700 yards from the gun. The radio transmitter powered up only after the shell had spun up to the correct rotational speed using a centrifugal switch. Multiple independent systems had to align perfectly before the weapon became dangerous. One failure in any safety circuit meant a dud shell that fell harmlessly into the ocean, protecting both the gun crew and the secrets inside the fuse. The first successful test came on August 12, 1942, when the newly commissioned light cruiser USS Cleveland conducted live fire tests in the Chesapeake Bay. During its shakedown cruise, radio-controlled drone aircraft served as targets. The results exceeded all expectations. Gunners shot down 3 drones with just 4 bursts on the first day. The drone aircraft were small, fast, and maneuvering. Yet, the proximity-fused shells destroyed them with ease. The test was so successful that the Navy led the plan's second day of testing and immediately ordered mass production. By January 1942, after 18 months of intensive work involving thousands of experiments, the team had produced fuses that exceeded 50% reliability in test firings. By PCE standards, this would have been unacceptable. But with American forces suffering severe losses to enemy air attack, 50% reliability of a revolutionary weapon was deemed acceptable. Production of the Mark 32 VT fuse began in November 1942. The first operational fuses reached Pearl Harbor that same month, traveling under heavy guard in sealed containers. The Pacific Fleet received 4,500 fuses by the end of the year, distributed only to select cruisers and battleships. The Navy security protocols surrounding the new weapon were extraordinary and unprecedented. VT-fused shells could only be fired over deep water where the depth exceeded 100 fathoms. Any dud that failed to detonate would sink to the ocean floor, taking its secrets beyond enemy reach. Ships received strict orders never to use the fuses where they might fall on land or in shallow water. The penalty for violating these orders was severe, including potential court-martial. Commanding officers had to personally approve each use. The fuses were stored in special magazines under Marine Guard. The technology was simply too valuable to risk any possibility of capture. In early January 1943, Helena put the new fuses to their first real combat test off Guadalcanal. The results exceeded all expectations. The ship's gunners fired only 22 rounds and achieved 2 confirmed kills at ranges previously thought impossible. A gunnery report filed after the engagement stated the value of the Mark 32 fused projectile cannot be too highly stressed. The Bureau of Ordnance had been waiting anxiously for exactly this kind of combat confirmation. Production ramped up immediately with contracts expanding from $60 million to over $200 million within months. Throughout 1943, VT-fused ammunition proved itself in battle after battle across the Pacific. Ships firing these shells downed enemy aircraft with unprecedented efficiency. During 1943, naval guns fired 36,370 anti-aircraft rounds. Although only 25% used proximity fuses, these shells accounted for 51% of all aircraft destroyed. The mathematics were stunning and undeniable. Time-fused shells required an average of 508 rounds to destroy one aircraft. Proximity-fused shells required only 155 rounds per kill. The new technology was more than 3 times as effective as conventional ammunition. The lethal fragment area comparison told an even more dramatic story. A 5 inches time-fused shell, if it exploded at exactly the right moment and position, could spray lethal fragments across roughly 60 square feet. This required perfect timing and positioning, rarely achieved in combat. A proximity-fused shell created a lethal kill zone of 3,000 square feet, guaranteed to detonate at the optimal distance from the target. The effective target area had become 50 times larger from the perspective of the explosive. An aircraft that would have flown safely past a time-fused explosion now flew directly into a cloud of deadly shrapnel. Night engagements revealed another crucial advantage. Time fuses required accurate range and altitude data to set the detonation time. At night, without visual confirmation, these calculations became even more difficult and unreliable. Radar could track aircraft position, but could not always provide the precision needed for time fuse settings. Proximity fuses eliminated this problem entirely. The shell found its own target regardless of visibility conditions. Night kill ratios increased by 370% when ships used VT ammunition. Japanese pilots who had previously used darkness as protection suddenly found themselves just as vulnerable as in daylight. Admiral William Holtze, commanding naval forces in the South Pacific, recognized the strategic implications immediately. Japanese torpedo planes had been making devastating nighttime attacks on American ships throughout 1942. The darkness protected the attackers and limited defensive fire to wild barges aimed at engine noise. With proximity fuses and radar-controlled gun Directors, this advantage evaporated overnight. Ships could engage aircraft effectively in pitch darkness at extended ranges. Japanese aircrew losses mounted dramatically. The tactics that had terrorized the fleet became suicide missions. By late 1943, Japanese naval aviation was suffering unsustainable losses, partly due to the proximity fuse's effectiveness. Yet even as Navy ships reaped these benefits, Army commanders in Europe fought with one hand tied behind their backs. They knew the proximity fuse existed. Intelligence reports and liaison officers had informed them of the Navy's success. They knew it could save their soldiers' lives. General Dwight Eisenhower, Supreme Allied Commander in Europe, had seen the statistics, and they had been refused permission to use it. The Pentagon's logic was based on legitimate security concerns that seemed reasonable at the time. Every artillery shell fired over land carried an inherent risk. Some shells would inevitably malfunction and fail to detonate. Some would fall in contested territory where German forces might recover them. If the Germans captured even one intact fuse and successfully reverse-engineered it, the consequences could be catastrophic. German engineers might develop their own proximity fuses for the anti-aircraft guns defending the Reich. The American and British strategic bombing campaign depended on being able to reach targets deep in Germany. If German flak batteries suddenly became 3 to 4 times more effective, bomber losses would become unsustainable. The air war over Europe would be lost. Intelligence reports suggested German science was fully capable of understanding and replicating the technology if given a working example. German electronics firms like Telefunken and Siemens had sophisticated research facilities. German scientists had already experimented with various proximity fuse designs, though none had reached production. There was also fear of German jamming technology. If enemy scientists figured out the radio frequency used by the fuses, they might develop electronic countermeasures. False signals could trigger premature detonation or prevent the fuses from working at all. The advantage would be neutralized and the secret revealed for nothing. Better to maintain strict operational security than risk these scenarios. So the Pentagon maintained its embargo through most of 1944. The Navy could use proximity fuses over deep water where duds would sink beyond recovery. But the Army could not use them in Europe where every shell mattered. This decision had devastating consequences measured in American blood. Time-fused artillery in the European theater continued to require thousands of rounds to achieve meaningful results. German formations moved with relative impunity because Allied artillery lacked the precision to stop them consistently. American soldiers died while a weapon that could save them sat in warehouses, waiting for authorization that might never come. Army commanders grew increasingly frustrated as 1944 progressed. They were fighting the Wehrmacht with inferior technology while a war-winning weapon remained restricted. General Dwight Eisenhower understood exactly what the proximity fuse could mean for his troops. He had reviewed the Navy's combat data showing threefold improvements in effectiveness. He knew that American soldiers were dying unnecessarily because of what he considered overly cautious security policy. And he was not a man who accepted unnecessary casualties quietly. The military situation grew increasingly desperate by late 1944. Despite successful D-Day landings in June and the liberation of France, German forces were far from defeated. They had stabilized their lines along the German border and were preparing a massive counteroffensive. Unknown to Allied intelligence, Hitler had assembled a strike force of 250,000 soldiers, nearly 500 tanks, and 2,000 artillery pieces in the Ardennes forest. The German plan, named Operation Watch on the Rhine, aimed to split the Allied armies, recapture the vital port of Antwerp, and force the Western Allies to negotiate a separate peace. On December 16, 1944, at 5:30 in the morning, Germany launched its surprise offensive. The attack began with a massive 90-minute artillery barrage that stunned American forces. 250,000 German soldiers supported by the secretly assembled tank forces smashed into American lines along an 80-mile front. The assault hit a thinly defended sector held by inexperienced and recuperating divisions. The 106th Infantry Division had just arrived from the United States. The 28th Infantry Division was recovering from severe losses in the Hürtgen Forest. German armored spearheads, led by elite SS Panzer divisions, penetrated deep into Allied territory. The weather was terrible with low clouds and snow preventing Allied air support. American forces reeled backward in confusion and near panic. The Battle of the Bulge had begun. American artillery fought desperately to slow the German advance, but time-fused shells proved woefully inadequate against infantry advancing across snow-covered open ground. Artillery observers struggled to provide accurate range data in the confusion. Too many shells buried themselves in the soft earth and snow, detonating harmlessly underground. Too many German soldiers survived. Artillery barges that should have destroyed entire units. German infantry advanced with confidence, knowing that American artillery, while dangerous, was not the precision killer it could have been. 3 days into the German offensive, with American forces in crisis, Eisenhower had seen enough. He sent an urgent message to the Pentagon through General George Marshall, Army Chief of Staff. Eisenhower demanded immediate authorization to use proximity fuses in ground artillery. He argued that the strategic situation overrode security concerns. If the Germans broke through to Antwerp and split the Allied armies, the entire campaign would collapse. The war would be prolonged by months or years. The risk of captured fuses, terrible as it might be, was less than the risk of losing the campaign. The Pentagon relented with remarkable speed. On December 21, 1944, all restrictions on proximity fuse use were removed. Within hours, 200,000 shells with VT fuses, codenamed POSIT, to maintain some operational security, were released from depots and rushed to the front lines. Artillery battalions received hurried briefings on the new ammunition. Most gun crews loaded the shells with no clear understanding of how they worked, only promises that they were far more effective than anything previously fired. The results were immediate and devastating. American artillery that had been marginally effective against German infantry suddenly became a precision killing machine. Shells exploded perfectly at treetop height without requiring any time fuse calculations. Every round detonated at the optimal height to spray fragments across the maximum area. German soldiers advancing across snow-covered fields found themselves in kill zones with no protection. Units that had felt relatively safe from time-fused artillery because heavy clouds prevented accurate observation now died in droves. The bad weather that was supposed to protect them made no difference to proximity fuses that needed no external targeting data. General George Patton commanded the Third Army as it drove north to relieve surrounded American forces at Bastonia. His artillery battalions received proximity-fused ammunition on December 22. The very next day, they put it to devastating use. Near Echenach in Luxembourg, a battalion of German infantry attempted to cross the Sauer River to reinforce their offensive. Patton's artillery caught them in the open. The new shells with the funny fuses, as Patton called them in his diary, killed 702 enemy soldiers by actual body count. The German battalion ceased to exist as an effective fighting force. Patton wrote a letter to Major General Levin Campbell Jr., Chief of Army Ordnance, expressing his amazement at the new weapon. The new shell with the funny fuse is devastating, he wrote. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 7,002. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first. This was not hyperbole from a man known for dramatic statements. This was sober professional assessment from one of America's most Experienced combat commanders. German soldiers captured after proximity fused. Artillery strikes described the attacks in terms of shock and complete helplessness. One prisoner from the 12th SS Panzer Division stated there was simply no defense against the new American shells. They exploded overhead with no warning, raining fragments straight down. Men in foxholes and trenches, previously protected from artillery that exploded on the ground, now died as steel. Fragments came from above. German commanders had no tactical response. They could not adapt to a weapon that eliminated the traditional defensive positions that had protected infantry. Since World War I, the 8th Infantry Division caught a German patrol in the Hirken Forest using a time-on-target barrage with proximity-fused shells. All 96 Germans were found dead. The patrol completely annihilated without a single survivor. Such devastating results multiplied across the front as American artillery battalions learned to employ the new ammunition effectively. German offensive momentum ground to a halt by December 25. The counteroffensive that was supposed to split the Allied armies and win breathing space for Germany instead became a catastrophic defeat that destroyed the last German strategic reserves. Allied anti-aircraft batteries also benefited dramatically from the lifted restrictions. German aircraft making desperate close support attacks suddenly faced the same lethal technology that had ravaged Japanese airpower in the Pacific. 417 German planes fell to proximity-fused anti-aircraft fire during the Battle of the Bulge period. The Luftwaffe's last major offensive effort collapsed under losses it could not sustain. Air superiority, always tenuous for Germany by late 1944, became completely unattainable. The port of Antwerp demonstrated another critical application of proximity fuse technology. The Belgian port was absolutely essential for Allied logistics, handling more supplies than all other ports combined. Its capture intact in September 1944 had been a major strategic victory. But the Germans responded with concentrated V-1 flying bomb attacks beginning in October. These primitive cruise missiles, essentially pilotless aircraft powered by pulsejet engines, flew at nearly 400 miles per hour at altitudes between 2,000 and 3,000 feet. Their speed and low altitude made interception extremely difficult with conventional anti-aircraft weapons. When proximity fuses became available for the anti-aircraft batteries defending Antwerp, the equation changed overnight. Modified fuses designed specifically for low-altitude high-speed targets turned the defenses into a nearly impenetrable barrier. In one 24-hour period, 48 of the first 75 V-1s approaching Antwerp were destroyed by proximity-fused anti-aircraft fire. The success rate climbed to nearly 80% as gun crews gained experience with the new ammunition. The vital supply port remained operational throughout the winter of 1944, enabling Allied forces to maintain their advance into Germany. Without proximity fuses, Antwerp would likely have been rendered unusable, potentially stalling the Allied offensive for months. The British capital also benefited enormously from American proximity fuse technology. London had suffered terribly under V-1 attacks beginning in June 1944. The flying bombs caused extensive damage and civilian casualties, threatening to break civilian morale. British anti-aircraft defenses initially struggled to intercept them effectively, destroying less than 20%. American proximity fuses rushed to Britain and integrated into British anti-aircraft guns transformed the defensive capability almost overnight. By the end of August 1944, anti-aircraft batteries equipped with proximity fuses were destroying 79% of all incoming V-1s. During 1 week in August, guns using proximity fuses destroyed 82% of V-1s targeted. London was saved from a weapon that might have forced consideration of evacuation plans. In the Pacific theater, the proximity fuse's importance grew even greater as Japanese tactics evolved into organized kamikaze attacks. By October 1944, Japan had lost most of its experienced pilots at the Battle of the Philippine Sea and other engagements. The Marana's Turkey shoot in June had cost Japan over 600 aircraft and most of their remaining trained aviators. Conventional attacks by poorly trained replacement pilots stood little chance against American fighter cover and ship defenses with loss rates exceeding 80%. Vice Admiral Takejiro Onishi, commander of the 1st Air Fleet in the Philippines, formerly organized the special attack units known as kamikaze. On October 19, 1944, the 1st unit, the Shimpu Special Attack Corps, consisted of 24 volunteer pilots flying bomb-laden Zero fighters. Onishi told the pilots they were already gods without earthly desires. Their mission was not to return. These units used aircraft as guided missiles piloted by men who accepted death as the starting point of their mission. The first organized kamikaze attack occurred on October 25 during the Battle of Lee Gulf. Lieutenant Yuki Oki led 5 airs against American escort carriers off Samar. One kamikaze crashed into the escort carrier USS St. Lo, detonating in the hangar deck among fueled aircraft. The ship exploded and sank within 30 minutes with the loss of 143 crew members. Other kamikazes damaged the carriers Santiswani Kitkan Bay and Kinanan Bay. The psychological impact on American sailors was profound and immediate. This was not warfare as they understood it. Naval commanders immediately recognized that proximity fuses would be critical against this new threat. Emergency orders went out to equip every ship possible with VT ammunition. Production priorities shifted. Ships heading to the Pacific received priority allocation of proximity-fused shells. Gun crews received special training on engaging kamikaze aircraft, emphasizing sustained fire at maximum range using proximity fuses to create a wall of exploding shells. The kamikaze threat was both terrifying and initially effective. Pilots who accepted death at the outset could not be deterred by defensive fire. They would fly through flak and fighters, absorbing damage that would force conventional attackers to turn away. They required only enough control to reach their target in the final seconds. At Leyte Gulf in October 1944, kamikazes sank the escort carrier USS St. Lo and damaged numerous other vessels. The psychological impact on American sailors was profound. Proximity fuses proved uniquely effective against kamikazes for reasons that became clear through combat analysis. The suicidal nature of the attacks meant Japanese pilots flew predictable straight-line trajectories directly toward their targets. No evasive maneuvers, no complex attack profiles, no last-second pullaways. This predictability played directly to the proximity fuse's advantages. 5-inch guns firing VT ammunition required only about 310 rounds per kill against kamikaze attackers, compared to roughly 624 rounds per kill against conventional strikes. The simpler flight path gave the fuses more chances to detect and destroy the approaching aircraft. The Battle of Okinawa, from April to June 1945, became the ultimate trial of anti-aircraft defenses against mass kamikaze assaults. Japan hurled everything remaining at the Allied fleet supporting the invasion. Nearly 2,000 kamikaze sorties targeted American ships over 3 months of brutal fighting. The Japanese labeled these mass attacks Kikusui, floating chrysanthemum, and launched 10 major waves. On April 6 alone, 355 kamikaze aircraft descended upon the fleet. The scale was unprecedented and initially overwhelming. American naval forces suffered the highest casualties of any Pacific campaign. 26 ships were sunk and 164 damaged. Nearly 5,000 sailors were killed and another 5,000 wounded. But without proximity fuses, the losses would have been catastrophic rather than merely severe. Nearly 2/3 of all VT fuses expended during the war were used in just the first 7.5 months of 1945, most of them in the waters surrounding Okinawa. Those fuses shot down more than 2,200 Japanese aircraft that otherwise might have crashed into American ships. The invasion succeeded, but at a cost that deeply influenced American planning for the projected invasion of Japan itself. Post-war analysis by the Operations Research Group concluded definitively that proximity-fused shells were 3 to 4 times as effective as time-fused ammunition in anti-aircraft roles. Some specific conditions showed even greater advantages. 5-inch naval guns firing standard time fuses required roughly 2,000 rounds to destroy a single aircraft under typical battle conditions. The same guns using proximity fuses needed between 300 and 600 rounds depending on the tactical scenario. Against kamikaze attacks, the benefit was even more dramatic, with some actions showing 5 to 10-fold greater effectiveness. The proximity fuse offered a psychological advantage as well, harder to measure, but no less real. Japanese pilots facing intense proximity-fused fire understood that even near misses could be fatal. The sky filled with airburst detonations that seemed to follow their movements with uncanny precision. German troops in Europe learned to fear American artillery in ways they never had before. The shells found targets that traditional rounds missed. They exploded at precisely the right height regardless of weather or terrain. There was no safe haven, no dependable shelter, no tactical counter. The proximity fuse also validated a revolutionary model of military research and development that would shape American defense policy throughout the Cold War and beyond. The project proved that civilian scientists, given sufficient resources and clear objectives, could solve problems once considered unsolvable. The partnership between academic researchers at Johns Hopkins, industrial firms like Crosley and Sylvania, and military planners produced a war-winning weapon in under 3 years from concept to mass production. The industrial effort was as remarkable as the technological breakthrough. The proximity fuse program stands among the greatest production feats of World War II, comparable to the Liberty ship program or the B-29 bomber initiative. At its peak in early 1945, more than 110 factories operated by 87 companies participated in fuse production. This vast network employed over 100,000 workers, most of whom had no idea what they were building. The production story began modestly. In August 1942, Crosley Corporation of Cincinnati received the first contract. Powell Crosley Jr., who had made his fortune in radios and refrigerators, converted his entire factory to fuse production in a matter of weeks. Security was extraordinary. Workers passed through multiple checkpoints. They wore color-coded badges limiting access. Mail was censored, phone calls monitored. Employees were forbidden to discuss their work even with relatives. Many assumed they were manufacturing improved radio tubes for military sets. Crosley's plant became a model of mass production efficiency. The assembly line was divided into stages, each worker performing a single task repeated thousands of times. One station wound microscopic coils, another soldered connections with exquisite precision. Inspectors checked every 10th unit. By December 1942, Crosley was producing 500 fuses per day. By December 1943, output reached 3,000 daily. At its peak in April 1945, Crosley alone produced 16,500 fuses every 24 hours. RCA joined production in September 1942, converting a facility in Bloomington, Indiana. Their radio manufacturing expertise proved invaluable. RCA engineers developed streamlined assembly techniques that cut production time by 30%. Eastman Kodak contributed more than assembly. Their precision optics and chemical expertise solved issues with photoelectric cells used in certain fuse variants. They also developed improved plastics able to withstand extreme temperatures. General Electric operated multiple facilities. Their plant in Schenectady assembled complete fuses, but their most critical contribution came from a converted factory in Cleveland that had previously produced Christmas tree lights. This plant manufactured the tiny tungsten filaments for the vacuum tubes, working at tolerances measured in thousandths of an inch. A single flaw invisible to the naked eye could cause fuse failure. Sylvania Electric Products became the backbone of tube production. Their plant in Ipswich, Massachusetts employed 10,000 workers across 3 non-stop shifts, pausing only on Christmas Day. The facility consumed enough electricity to power a small town. Air filtration systems removed dust that could ruin tubes. Workers wore anti-static clothing. The plant produced 95% of all proximity fuse tubes, manufacturing roughly 1 million tubes every 2.5 days at peak output. By war's end, Sylvania's Ipswich facility alone had produced 5,683,032 complete fuses, more than any other site. Dozens of specialized firms supported the effort. McQuay Norris in St. Louis produced metal components. Zenith Radio Corporation assembled electronic modules. Wurlitzer, known for organs and jukeboxes, built precision timing mechanisms. Even the Lionel Corporation, famous for toy trains, manufactured specialized parts. Each company contributed unique expertise that helped solve complex production challenges. By war's end, American industry had produced 22 million proximity fuses at a total cost exceeding $1 billion in 1940s currency. The cost per fuse dropped dramatically as mass production improved. Early hand-built fuses cost $732 each, more than many automobiles. By 1945, assembly line refinements reduced the price to $18. This 40-fold reduction made widespread use economically feasible. Even at $18 per unit, proximity-fused shells were cost-effective considering their vastly improved kill rates. Quality control was uncompromising. Every batch faced exhaustive testing at multiple stages. The National Bureau of Standards operated dedicated facilities. Fuses were subjected to temperature extremes from -65 degrees Fahrenheit to +160 degrees Fahrenheit. They endured humidity chambers, salt spray tests, vibration tables, and centrifuges simulating firing conditions. Random samples from each production lot were actually fired to confirm functionality. Failure rates had to remain below strict tolerances. Any issues triggered a review of the entire run. This meticulous oversight ensured reliable performance in every climate, from Arctic cold to tropical heat. The secrecy surrounding the proximity fuse held remarkably well. Despite millions fired in combat, Axis powers never reverse-engineered the technology or developed effective countermeasures. German engineers captured a few dud shells in late 1944, but refused to believe the fuses actually functioned as described. The idea that radio equipment could survive the shock of being fired from an artillery piece seemed so implausible that they assumed the examples were decoys. They wasted resources studying countermeasures for fusing methods the US wasn't even using. The Japanese faced even more severe limitations. They captured several dud shells during Pacific campaigns, especially from naval bombardments that landed ashore despite regulations. Japanese scientists grasped the principle but lacked the industrial base for the extreme miniaturization required. Their electronics industry simply could not match American capabilities by 1943, and even with working examples, Japan had no realistic path to production before the war ended. Secretary of the Navy James Forrestal later wrote that the proximity fuse helped blaze the trail to Japan. General Eisenhower declared in his memoirs that if the Germans had perfected and deployed proximity fuses 6 months earlier, the invasion of Europe might have become exceedingly difficult, perhaps impossible. These were not casual remarks, but strategic judgments by leaders who understood how narrow the margin between victory and defeat could be. Yet for nearly 2 years, Army commanders were denied access to this war-winning weapon because of institutional caution that, while understandable, ultimately proved excessive. The Pentagon's security fears were legitimate, but the continued embargo meant American soldiers died with inferior equipment, a failure of strategic judgment that prioritized hypothetical future risks over immediate battlefield reality. Only during the desperate days of the Battle of the Bulge did leadership approve what should have been authorized long before. The proximity fuse represented more than a weapons breakthrough. It marked a fundamental shift in how military technology could be conceived, engineered, and deployed. It proved that electronics and automation could enhance conventional weapons to extraordinary effect. It showed that even small technological advantages, when properly leveraged, could determine the fate of entire campaigns. Most importantly, it demonstrated that innovation demands not only scientific brilliance, but massive industrial execution and the institutional courage to field new capabilities despite inherent risks. The sailors aboard Helena, who fired those first operational shots in January 1943, could not have known they were inaugurating a new era of warfare. They simply knew their shells were destroying targets previously thought untouchable. But the officers who commanded those forces, the generals who directed them, and the admirals who assembled fleets around their capabilities understood that something fundamental had changed. Warfare had entered a phase in which technological sophistication mattered as much as bravery or numbers. In less than 3 years, American researchers and manufacturers created a weapon that reshaped warfare, produced it by the millions, deployed it across 2 continents, and used it to help win the largest conflict in human history. The weapon the Navy first kept to itself became the weapon that helped save the Allied cause when it mattered most. The innovation the Pentagon initially feared to deploy became essential to victory. That progression, from impossible to indispensable, stands as a testament to what human ingenuity can achieve when the stakes are survival. The proximity fuse reminds us that transformative military advantages require overcoming not only technical challenges but institutional inertia. Innovation delayed costs lives, but once unleashed, revolutionary technology can alter the course of history itself. The legacy of the proximity fuse extends far beyond World War II. Every modern anti-aircraft missile uses proximity fusing. The Patriot missiles that intercepted Scud rockets in the Gulf War relied on proximity fuses derived directly from the Mark 32. Naval close-in weapon systems like Phalanx use proximity fusing to defeat incoming missiles. Air-to-air missiles carried by fighters worldwide detonate using proximity-fused warheads. The technology pioneered under wartime urgency became foundational to modern air defense. The scientists who created the proximity fuse shaped American science for generations. James Van Allen later discovered the radiation belts that bear his name. Many Section T researchers became leaders in the space program. The Applied Physics Laboratory at Johns Hopkins, born from the Proximity Fuse Project, remains a major defense research institution. The model of collaboration between universities, industry, and government became the blueprint for Cold War technological development. Most importantly, the proximity fuse saved countless lives. Naval historians estimate that without proximity fuses, American casualties in the Pacific would have been 30 to 50% higher. The kamikaze threat might have forced cancellation of the Okinawa invasion. The planned invasion of Japan in November 1945 might have faced insurmountable losses from suicide attacks. In Europe, the Battle of the Bulge might have succeeded in splitting Allied armies. London might have been evacuated under sustained V-1 bombardment. The war might have lasted into 1946 or 1947, with millions more dead. The proximity fuse stands as proof that sometimes the most crucial victories arise not solely from courage, though courage is indispensable, but from the union of scientific innovation and industrial might. 22 million miniature radars, each no larger than an ice cream cone, helped win the greatest war in history. They did so by solving a problem that had once seemed unsolvable, turning the vast sky into a lethal barrier for enemy aircraft and giving the Allies the edge they needed when they needed it most.